So thank you very much. It's an honor to speak here, even though that our company is not truly working on microbiome. So David was mentioning it. We are basically trying to race against the antibiotic resistance that is appearing all over the world. So we developed a diagnostic device, antibiotic susceptibility test, it's a phenotypic test that other than other antibiotic susceptibility test is not based on growth or molecular testing. It's based on bacterial nanomotion. So that's new technology. I will talk a bit about the company because Resistel, probably not everybody of you know about us. Then I will talk about the technology and show you some data. So we have only 10 minutes, so I might race a little bit, similar to the antibiotic resistance. So the company is roughly 5 years old. Now I think we're approaching 6 years. 2018 was founded. We are roughly 30 people. Our database, where these nanomotions are basically recorded, are 15,000 experiments. So we are building a database. We heavily involve machine learning. We have 5 patents. Give you an idea, because I think some of you are also here for understanding a bit startups, what the funding situation of such a startup is. So at the moment, we have raised roughly 20 million. Okay, this is the team. So we are heavily involved in microbiology, data scientists, and engineering. So startups are involved in development, our company at least. And then we have an advisory board reaching out to people in Europe, and especially CHUV. So you see the space here, biosafety cabinets, and now maybe what are we actually worried about is antimicrobial resistance. And I think everybody who works with antimicrobial resistance knows about this publication, citing that up to 5 million people these days are dying every year, and antimicrobial resistance is involved in these deaths. So it's a quite huge number, and in 2050 we expect these numbers. So these numbers will rise. So there is no way out of this. Our technology, as I said, is basically a fast AST. So we want to be delivering results fast. And the use case here is bloodstream infection. So if you get basically a bloodstream infection, that your state can actually deteriorate quite fast. So your bloodstream infection, PSI, can go to sepsis, septic shock, and potentially to death. The clinicians have no idea in the beginning of the treatment what infects you, what are the antibiotic resistance profiles, so they treat empirically. And the current methods allow you basically to know about the antibiotic resistance or the bacterium that infects you after 1 or 2 days. Like in Switzerland, it's usually 2 days. It can be up to 3 days in other countries, less developed countries. So this is a diagnostic pipeline that's obviously very late when the clinician knows which antibiotic I actually should use. So in the beginning, as I said, it's empirically. It could work, it could not work. Our suggestion is you start with a positive blood culture that is basically always taken from patients with bloodstream infections. If it turns positive, you do a MALDI-TOF species identification, and then usually you have the standard test run that take 24 to 48 hours, or you run our device that gives you the result in 2 hours. So instead of 2 days later, you would basically, the day of the positive blood culture, you could get the result. Okay, so I mentioned nanomotions. So we measure vibrations of bacteria. So nanomotions doesn't mean anything else by vibration of bacteria. They're usually the heaviest in the low frequency range. Every cell does this, so it's a phenomenon that is based on metabolic activity, cellular processes. So bacteria just do that. We have developed sensors, a hardware component, Phenotech device, which you can also see outside. So Matthias and I will be outside in the break, so you can talk to us if you want to know more about it. And also a big component is software. So our technology not only measures vibrations, we also need to make sense out of these patterns. So there is data acquisition software developed in our company, and also a big part is due to machine learning. So there's a big part of data science. And these algorithms that we come up with then can be used in the clinic to classify a patient sample you have susceptible or resistant infection. So this is a little workflow that we also apply in the company to train those algorithms. I will talk a bit more in detail about the actual components here. So you have sample preparation, you come from a blood culture, you measure your bacteria on the sensor, these vibrations, as I said. You use the data that you get out of this to develop algorithms. These are classification algorithms that withdraw information from whatever clinical isolates you measure, you build a classification model with these information that then can be used in the clinic. Okay, so this is the heart of the technology. So we measure vibrations with a cantilever. So everybody who has done anything on atomic force microscopy knows cantilevers. It's a little lever, it's a little springboard that you also discover when you go to the swimming pool. You have bacteria attached to these cantilevers, and now the idea is they're metabolically active, they vibrate a lot. You challenge them with an antibiotic, you have the case of susceptibility or a case of resistance. Susceptibility, these vibration goes down, resistance, these vibrations continue or even go up. And you measure that with a light source. So if you want details, I can talk with it about outside. It's a technology that originally comes from EPFL. So bacteria sit on this cantilever on an interaction between positive and negative charge from the surface net charge of the bacteria. So the bacteria are just sitting on it. They're in a gel-like environment. Here you see an electron microscope picture of these bacteria on the cantilever to have an idea of the dimensions. And these are the recordings. So in the left case, you see a susceptible case, and in the right case, on the right side, you see the resistance. And you see, actually, just looking at these two graphs, they show you basically the vibrations over time that both look very different. So just looking at these two reference strains, it's very easy. But to basically apply the technology to all these clinical isolates that are out there, you need machine learning to withdraw information from those graphs. Again, I can tell you more in detail if you're interested outside, to build these classification models. So usually we have like 200, 300 different clinical isolates with different MICs, record them, get a classification model, usually based on 1,000 recordings or something like this. And they are in the clinic now, basically validated. I cannot talk about clinical data because the clinical studies have not finished yet. This is an example how those classification models are built. So we're looking here at a last resort antibiotic that not yet has developed a lot of resistance, ceftazimab avibactam. It's a drug that is distributed by Pfizer. You see on the left, basically, the data set that we used for training those algorithms. So you see the number of strains. I actually can use, wait, does it work? Yes. So on the left, you see basically the histogram of the strains we were using. And on the right, you see our classification model. We train a classification model, the scores that are assigned to it. So on the x-axis, you see the MIC, so this is done by reference methods. And then our score gives positive values to susceptible and gives negative values to resistant experiments. And you see basically how they distribute over the x-axis. So you see the blue ones are correctly classified as susceptible, the red ones are classified correctly as a resistant one. You see there are some false classified, but overall, within 2 hours, you get a well-classified data set. You can test such a classification model on a test set, so you basically use different isolates, measure them again, run your algorithm, and see how well it performs on this unseen data before. So I think that's a classical validation method for machine learning. I don't have to go too much into detail. But you see also this model seems to be general enough to test an unseen data. So these are preclinical data. It's a rather small data set. So for the clinical validated models that I just mentioned, we're talking about like 1,000 experiments. So here we're looking at 43 experiments. So anyway, so these classification models work quite nicely. After 2 hours, you get the results. So here, these are basically the values that you use to assess such AST. So we talk about the training. We had a 95% classification accuracy, and on the testing, 93%. So basically what the FDA and other regulatory bodies need from these ASTs. So it's very fast, much faster than others, and quite accurate. Just to show you an example. So now this technology, we're not only doing AST, it's a method, that's why I also called it phenotypic assessment using nanomotions. So it's a technology we work very heavily with CHUV. So they're interested in urinary tract infections, they're interested in tuberculosis, and they're also interested, Gilbert Greup, who is part of this consortium, particularly interested in sexually transmitted diseases, so chlamydia research. TB, as you know, is a very slow-growing bacterium. Chlamydia is actually outside of cell culture, not growing at all, so you can all assess metabolic activity with such a method. So it's a really growth-independent method, so it's a very big advantage of this method when you work with challenging environments, and I think microbiomes could be also measured with this. Yes, so our main indication is bloodstream infection, but all these other indications that you see here we also work on those with different intensity. Okay, so coming back to this company, so also talking about the company, what we are doing. So we have the research device that is outside. So this is something that if somebody is interested, could talk with us if some want to measure something in their indication. And we have a fast AST for this last resort drug. We're developing a multi-channel device. So these are basically the developments of the company right now. We have different patents. We collaborate extensively. So we also now in a JPI AMR consortium with the University of Exeter, Tartu University, also CHUV, and Ramón y Cajal University Hospital in Madrid. So I think we are well connected, and that's it, basically. Thank you.
So
do we do discussions?
A few questions, please.
So to everybody, you have a microphones built in your seats. So look for the microphone for us.
Fancy.
Thank you, Rob.
Okay, fantastic. Sorry. One question, can you distinguish between different modes of action of antibiotics with the different vibrations? I imagine that depending on where they kind of inhibit.
Yes, so we actually tried this for fluoroquinolones and for cephalosporins, and you could, I think we had 85% accuracy on that data set, we could distinguish susceptor restraints. So I'm quite optimistic that we can actually expand on that. So I think it's a good application to also distinguish molecular mechanisms of actions. Yeah. Yes.
Does it also work if you have a mix of different strains of the same type of bacteria on your?
So we have not really investigated that. Like not enough experience or done enough experiments to really comment on that. In bloodstream infections, you usually have this is our main indication, right? You have a single species because you culture, right? We face this challenge a bit with UTI infections because this is not a culture in that sense, so you have definitely contaminations. Yes, I don't know, that probably depends a bit what you would like to address, right? So depends a bit on your question. So I think you can measure maybe interaction with different bacteria species and exchange them and probably see differences. I assume, we haven't done that, it's not our question. Mm-hmm.
To which extent do you require cultivation of the bacteria?
So, as I said, bloodstream infections usually have a blood. You cannot come from blood because you don't have enough bacteria in blood. I think this is from UTI. We don't culture at all. We start directly from urine. I don't consider this a culture. We can measure non-growing bacteria. So there's a manuscript in actually needs to be submitted for really non-growing E. coli. So they are artificially induced to not grow, and you can measure those. Yeah.
Any last question?
Okay, thank you very much.